Hello, and welcome to Autodesk Build Your Moldflow IQ webinar series. Thanks for joining us today, but we're happy to see all these familiar faces here today. Before we dive into today's topic, I'd like to just review a few logistics. First, we have an hour time slot booked for this today. However, from the past couple webinars, and for those of you who were able to attend those, you may have noticed that it's typically between 20 to 30 minutes long. And then we like to also include a live question and answer session at the end of it. So feel free to sit through it. Throughout the webinar, you may also enter in your questions using GoToWebinar's question section down below. And any questions that we aren't able to answer during this webinar, we do ask you to please post these within the Moldflow Insight forum, and either myself or one of the other experts will be able to help you through those. This webinar will be recorded, and we will be posting it to the simulation community website shortly after the webinar. Caitlin Shappett is joining us today, and we'll be reviewing how to utilize Autodesk Moldflow Insight towards improving plastic part quality through a design of experiments. So Kate, I'll pass it over to you.
Thanks, Kristen, and welcome everyone. So for those of you that do not know me, just a quick introduction. My name is Caitlin Shappett, and I am a plastics engineer who has worked with Moldflow at Autodesk for over 6 years now. I graduated from Penn State Barron with my plastics engineer, and in my spare time, I am a dog walker extraordinaire, as you can see here in this picture. Or maybe in this case, getting walked by said dog. Currently, I work on the simulation technical sales team. As mentioned today, we will be discussing the use of Moldflow to optimize part quality through a simulated design of experiments, frequently referred to as DOE. We'll do a brief overview of what a design of experiment is, how to perform one within Moldflow Insight. Next, we'll take a deep dive into how Moldflow's quality tools can be used with the DOE to mold higher quality plastic parts through an example. After running through some final tips and tricks, we'll go through some live Q&A. Jumping into what a DOE is, the concept can realistically be applied to concepts in any industry, not just injection molding. As shown here, a DOE is defined as a systematic approach for understanding the relationships of inputs against specified quality criteria. Essentially, when I change something, how does it affect the things I am most concerned about? Today's world is all about data, so when viewing a DOE in the field of scientific injection molding, this is how you can log a tremendous amount of data to help with improving your molding processes. It provides a holistic view of how each of the machine settings influence the end product. This enables the process engineer to hand over those influencers to the manufacturing team when the mold goes into production to create more informative process settings and instructions to better prepare them for handling part quality concerns that may appear during production. When we jump into running a simulated DOE for injection molding, let's first understand which Moldflow works best. A DOE consists of running several versions of your original setup, and the number of runs is determined by the number of factors you plan to change. Because this is a more scientific way of analyzing their effects, the setup of each of those runs involves changing just one thing at a time while compiling on top of their changes. This means you may find you need to run 64 separate runs. Now, you can technically run through a DOE using Moldflow Advisor or Insight Standard. However, that would require manually duplicating the study each time and changing variables yourself, then compiling the data manually, identical to if you were running at an in-person DOE at the machine. This, as you know, is very time-consuming, and it is critical you record what you do each time so you can keep track. So it's not ideal, but it is doable. The better option is to use Moldflow Insight Premium or Ultimate, which contains an automated DOE builder, which guides the user through assigning factors and quality criteria. It then automatically creates each of those different studies runs them simultaneously, and then presents the data in the tables and visual result plots. Simulating a DOE has its advantages. One is it provides the ability to multitask. Let's say if you are in the lull waiting for a mold being built, spending a few minutes to set up a virtual DOE lets you focus on other projects while it runs. Then when the mold build completes, you have that background understanding of which variables are influencing your part quality. It can also run those separate experiments simultaneously. So if you run on the cloud or on a server with identical solving power, time savings from that can be a big benefit. Something that you cannot do if manually running a DOE. Another advantage, hinted in my previous comments, is that the purpose for setting up a virtual DOE is simple. If you've already set up and run the Moldflow analysis. If you use Moldflow during the part and mold design changes, adding a DOE to the existing simulation involves setting up the type of DOE, variables, and quality criteria. And since it duplicates your original study on those inputs, the existing simulation is untouched, just some new added results. The cost behind in-person DOEs can be exponential if you're tying up press time, not only during running, but the time for the mold temperature to equalize, wasting a good amount of material. Since you can't use those parts and tying up metrology resources to measure and compile results, not to mention the engineer's time interpreting those results. Simulation enables you to minimize these costs by either eliminating the need for a physical DOE or at least reducing the number of runs or parameters changed. One last advantage that I will cover today is the one mentioned previously, the data. If you're a data person, you live by Excel spreadsheets and love digging through those numbers mean. This type of simulation is right up your alley. Within Insight's DOE tools, you aren't limited to only what is listed within those wizards. There are just the most commonly used inputs when it comes to factors and quality criteria. For example, one thing we'll touch later today are critical dimensions as factors and flatness or roundness as quality criteria. So let's move on and take a closer look for the process of setting up a DOE inside of Moldflow Insight. We will walk through how to set up the DOE from the beginning. First, you have to select the type of analysis you want to run, whether it's a cool fill pack warp, a fill pack warp, or maybe just a filling analysis. This is determined by what you are trying to question and the answer you are trying to get, which plays into your part specifications, for example, your quality or your critical dimension. Then you select the type of DOE you want to run. Again, what type of questions are you answering? This at a high level is what the DOE builder looks like, and I'll dive in much deeper into what each tab means. But for example, you can change things like the cooling inlet, which allows you to then specify a range of inlet temperatures. And these are a bunch of other variables and criteria that you can change within the DOE builder. Diving just a little bit deeper, depending on the types of questions you can actually set up and why you might want to set these type of analysis up. So on the left here, we can see the critical dimensions, and these allow you to measure from node to node within the quality criteria. So setting these up prior to running the DOE is important. On the right, by making geometric modifications, it allows you to investigate the effect of modifying one or more CAD features by automatically running an analysis for each of the CAD geometric modifications you specify. This provides you with more detail on how to best manufacture your part and keep addressing your specific constraints. You can, for example, create flow leaders and analyze the difference with your original model. Additionally, you can set up roundness and flatness node lists to optimize your part and understand how different process settings affect how these rounded components change shape following a warp analysis. Similarly, you can isolate the flatness if there's a concern for a portion of the part, such as a sealing surface on an assembly plane. As mentioned earlier, I wanted to dive deeper into the actual DOE builder and the types of simulations and experiments that you can run using the DOE. So the first one that you can choose from is one variable, and this experiment calculates the effect of a single variable on a set of criteria that define the part quality. The result is an XY plot of the effect of the chosen variable on each of the selected quality criteria. This analysis is recommended if you are only interested in a single known variable. The one below that, variable influences, ranks the impact of several variables on a set of criteria that define part quality. This analysis is recommended if you need to know which variable have the greatest impact on the part quality. The next, variable responses. This analysis uses a face-centered composite design to look at non-linear interactions between input variables and set up criteria that define part quality. This result is a response surface plot, which shows how sensitive each selected criteria is to the selected input variable. And then lastly, variable influences, then responses. This is the one that we'll take a deeper dive into today. The one thing I do want to note here is that you can specify the number of variables to transition from, whether it's 3, 4, or more. And in this example, I specified 3. This one combines the previous 2 experiments, so the variable influences and variable responses, into one, and is recommended if you would like to perform an extensive test to see how sensitive select quality criteria are on those variables that have the greatest impact on part quality, but if you are unsure of which variables have the greatest impact. Diving deeper here to the next tab. So first we looked at the experiment tab. Next, we're looking at the variables tab. The left side panel lists the input variables that you can select to study. The right side provides you with an opportunity to change the experimental range for each variable. Select each input variable that you are interested in and accept the default values, or you can change them if you prefer. One thing to note here is the minimum and maximum values must be symmetrical about the middle value, which is automatically updated for you. The next tab, the quality criteria tab, this tab is used to select which analysis results you would like to study within the constraints you have selected on the variables tab of the DOE builder. The greatest thing about the DOE builder is it provides a description of how the criteria is calculated. Additionally, once you have created your custom warp criteria, flatness and roundness node scripts, your critical dimensions bars, you can add those to these tabs. So how can you run a DOE in Moldflow? Running a DOE virtually, it allows you to run many, sometimes 23 analyses to gather insights into an experiment. And there's several ways that you can solve these. You can solve locally versus the cloud versus a server. DOE solves will run based on available hardware and licenses. For Moldflow Insight Premium, you can solve 3 jobs at a time locally. On the cloud, there is an infinite hardware and licenses, so you basically can run all 23 analyses simultaneously. And then you can also run on an HPC or a server machine, if you have one, that will allow you to run, it reduces the solve time, not necessarily always faster though. They're more of a capacity solution. So this is a high level of the type of information. And again, I will dive much deeper into what this means. But after you've run a DOE, there's a couple places that you tend to get the information. The log, which gives you the variable influences and variable responses information. And then you can also get the actual visual results that we're more accustomed to. So response surface plots, for example. For this example, and for those of you who may not know Tim Vanest, who's on the line, he gave us a really great example from the Moldflow Summit presentation earlier this year. He has this story about how he is painting a room in his house, and I think many of us here know how to paint and have painted before. And like all of us in the plastic industry, we tend to take note of the plastics around us. Anyway, he saw this lid and realized how easy it would be to design and build that mold, but then quickly retracted that thought. After examining the part, he noticed the obvious centrally located gate and the addition of the offset center hole, and introduces non-uniformity cavity filling, which he ran through Moldflow and had potential to cause difficulty with filling the outer rims while achieving the high quality part. And you can kind of see in this example, it takes about 1.5 seconds at end of fill on this side opposite of the pour spout, whereas it takes maybe 1/2 second to fill over here closer to the pour spout. And the simulation, of course, confirmed this offset fill pattern, but also when reviewing the part geometry more closely, a new concern was introduced. In addition to the gate not being located necessarily at the center of flow, it is also not located at the thickest region, as we can see here where it is the thickest at the pour spout versus in the center, which is 1.5 millimeter. The dimension scale factor, which we'll point out a little bit more, is the spout region. And again, that's the thicker area. So one thing when you're filling out the DOE builder is always to keep in the back of your mind what is important, what is the quality that's important that we need to maintain. So in this example, a lid has to be assembled to the rim of the bucket. And you can see here the critical dimensions and the nodes that were selected during this experiment, highlighted in yellow. Additionally, when assembled to the bucket, sealing is important. If you accidentally knock the bucket over, you don't want your paint to spill out unintentionally. So flatness becomes important, and we can very easily in Moldflow select various regions of the part to determine how these impact one another. Here we're looking at the flatness of the center of the lid versus the rim of the lid versus the roundness of the lid, highlighted in red here. In this study, we ran, as I mentioned earlier, a variable influence then response, because it tends to be where you're going to get the most information about your experiment. If you remember earlier from my description of what you get, this is performed when you would like an extensive test to see how sensitive select quality criteria are on variables that have the greatest impact on the part quality. And in this particular case, the variables that were chosen because we know these can have the greatest impact on our criteria, which in this case is mostly pertaining to warpage. So diving a little bit deeper, I mentioned there's various ways to get results out of a DOE, and the first place that we're going to look is the log file. So taking a look at the log file, you get a lot of information that you need to be able to interpret and understand really what you're looking at. So that is what we're going to do here today. And the first set of results that you will get are with respect to the variable influence. So we, for example, can look at roundness, and you can see that the two largest impactors of roundness are the dimension scale factor, so the spout thickness, as well as the filling control, followed by a close third of mold and melt temperature. Now, if we look at a completely different set of quality factors, for instance, the distance between those nodes, you can see a different set of influences. So here, filling control has the greatest impact versus melt temperature. And then lastly, the global weights are tied into the variable responses analysis. And in this case, the dimension scale factor, melt temperature, and filling control are the highest impactors and have the greatest influence. Again, earlier on in the DOE builder, we set the highest influences to 3 when we set up the DOE. So when we interpret the variable response information, for optimum quality on flatness, these are the process settings you would use. The other thing to look at here is the range. The range in this example of the flatness can vary anywhere from 4 millimeter to 8.7 millimeter. So really this is a gut check for knowing if it's good or bad based on your part's specifications. So if this, for example, needed to be within 0.1 millimeter, you would never get close to that. Diving into additional results that we can look at are the XY plots that you get. So when we start looking into these kinds of DOE results, and in this example, for the lid example, the spout region where you would pour the paint from was thicker, as I mentioned earlier, than the nominal wall. This is essentially creating a flow leader around that area, resulting in the uneven filling. With the DOE, we are able to see how effectively we can create a uniform filling cavity through automated thickness adjustments, referred to in Moldflow as the dimensional scale variable. This result is an XY plot, which is interactive to see the injection pressure changes as the process controls are modified, depending on the part thickness in that region. This helps us to understand how much of a thickness change we can make to that flow leader to basically offset the faster filling effect, thus provide uniform fill. So when an analyst is looking at this, they can conclude that at the 225 Celsius melt and 1 second of fill time, the injection pressure is lowest around 25% increase of the wall thickness. So if we remember, the nominal wall was 1.5 millimeter earlier, and it doubled at the pour spout region. Did we need to increase that wall thickness as much at the pour spout region? So really this means with the wall thickness increased from between 5 and 35%, which is quite a bit. So at the end of the day, how much thickness offsets the flow leader restriction is basically what this says. Then when we look at response plots, everybody's favorites, such as this one for roundness of the spout region of the lid, the result plot is essentially showing numerous data points plotted on 3 axes for a specific point in time. And you can see those kind of highlighted right here with my little arrows. That means you can see the interaction of 2 variables on the quality criteria, which is plotted along the z-axis. The thing to look at here is for a small slope or even a flat area, which represents a more stable change between process settings. So looking at this result of roundness for the lid, we've been reviewing, and analysts would review this and find that at 1 second fill time, the melt temperature does not affect part roundness at all. Note that the flat plot when looking at the YZ plane, you can realistically replace the y-axis with another setting in this case to see if others may have more of an effect by simply selecting the y option in the response plot settings. So you can change these down to a different setting. And then in the XY plane, it is a bit of a different story here, as we can see the parabolic curve, meaning the roundness gets worse as you vary more and more from the original part thickness, represented by the 0% point. This is another example of a response plot where, in this case, the sliders for adjusting variables display the result directly on the part geometry. It is just like if you were running all of those variables in separate studies and then comparing the deflection result against one another. So it is a little easier to interpret the results from than the previous response plot. With the lid, an analyst can interpret these results so that they identify that, again, the wall thickness is resulting in effect to part quality. Increasing the wall thickness resulted in less warpage, while decreasing wall thickness increased deflection by several millimeters. So it's a bit of a trade-off, really, but you have to remember to stay within your part specifications. So as we wrap up here today, just some quick DOE tips and tricks. So the first here is minimize the element count of your model to reduce the solve times. As we all know, when we're running, whether it's a fill pack analysis, the number of elements you have in your mesh increases the time it takes to solve. So if we can minimize that, that's a benefit to you. Then running multiple DOEs with fewer variables solves faster than one DOE with lots of variables. Warpage results, as we all know, are unique. Minimizing small dimensions could mean the most warpage. How and what do you do about that? Run a DOE, but ignore log file results. You can also use the slider bars to find the real information. And then, like any simulation that we run, DOEs can be an iterative process. You may need to solve one to better understand what is happening in your part and your process. Then you may need to change a variable or a quality criteria and rerun it to understand how that impacts your part and process. So just some wrap up today. We better learned what a DOE is, how does it help you, how to actually set it up, and what the information in the DOE builder means. And then lastly, how to interpret those results. I know when I first started getting into design of experiments, interpreting the results, whether it is a DOE or just regular results that you get from a single analysis, can be cumbersome at times. So, my point today is to really set it up step by step and dive very deep into what we're looking at and what the data actually means.
Thanks, Kate. That was a great presentation, hopefully very informative to all of those who are on the call today and for anyone who's watching this recording later on. With that, I do want to go ahead and thank everyone again for joining us today. And again, follow up with any questions on the Moldflow forums. Thank you.